All right, so we want to, with a perceptron, we want to be able to start off with some arbitrary weights, maybe completely random weights, maybe some weights that are like, we kind of know that it sort of works, but it's not exact. And we want to be able to let the system figure out how to update those weights and do the right thing. So again, we're going to be looking at the examples of just a single perceptron. And we can, again, think of this in the context of OR that we started with. Right? But OR, we built this just by thinking through. So what will we have? We will have an x and a y value. We will have a bias of 1. And we have some weights. And these weights can be arbitrarily assigned. And again, I'm calling that bias weight W0, even though I'm putting it at the end. All right, so to update the weights, we are, first of all, going to think about an update rate. And an update rate is how much of the potential change in a weight are we going to use at any one given time? So the update rate, which mathematically we tend to write as alpha, on the other video, we were using whatever Blackboard Collaborate thing was built in, and it was just typing on the screen. Not very good approach. And so I wrote the word alpha out in that case. But we have an update rate. And so what could the update rate be? The update rate could be anywhere from 0, which is 0%, to 1, which is 100%. What if your update rate is 0? Then it's not updating anything. So whatever weights you start with are the weights you're going to finish with. What if your update rate is 1? Then you make all of the possible changes that you can make every single time. And what might happen, you might do this thing that we saw with genetic algorithms where they sometimes focus in on the wrong answer and they get stuck on the wrong answer. Or something else that can happen is if you make all the possible changes you can make and then you switch to a new test or a new training value, it might undo all of that. And then you go back and it puts it back, and then you go back and it takes it back. And so you get stuck in this kind of oscillating thing that doesn't really settle down. So what do you want? You want your update rate to be somewhere between 0 and 1, some percentage that's usually not too big but not too small. What is too big or too small? Oh, that depends, right? And so we sometimes have to tweak that and figure out what's a good update rate. All right, so that's part of the calculation, a rate that we determine that tells us what's happening. Again, alpha is between 0 and 1. We don't want it to be 0 unless we already have the right answer, but that's never the situation. And we usually don't want it to be 1 because that can cause other problems as well. But it can be. There's nothing that says it can't be. It's just we don't usually want to do that. No, it's how, we'll see in a second when we put it into place. It's how you have a certain amount of change that you can make, and it's what percentage of the possible change do you actually implement. So we'll see it in just a second when we put it into place. It's like we're looking at binary output in this case. So the answer is supposed to be 0 or it's supposed to be 1, and it's not. So you can change your input by, or you can change your value by this much. Here's how much change you're able to make. How much of the possible change do you actually make at a given time? All right? All right, so here's what happens. We have our function, the Heaviside function, was h of the input, right? That involved the dot product with the weights. So what we're going to do is weight I for the update portion is we're going to take the old weight and then make a change to it. All right, what change do we make? Well, the change that we make involves the alpha. And now let's think about what happens. Over here, we know what the right answer is because it's training data. We know what the right answer is that corresponds to a particular input. So we're going to take the right answer and subtract from it what? Subtract from it the answer that we got from the function. Right? The answer from the function is a 0 or a 1. We take the right answer and subtract that answer that we actually got. So what is this? This is how much error there was in our answer. And then we multiply this by that particular input. All right, so let's see what happens. On some iteration, we have a current weight in place. With that weight in place, we see what the answer was, what the perceptron gave as the answer. Subtract that from the real answer. Multiply this by the alpha. Multiply that by the weight, or the input value itself. That gets added onto the old weight, and the old weight gets replaced. So what will that do? This is how wrong the old answer was. This is how much of that we want to utilize at any given time. If that's a 1, we're going to take all of that into consideration. If it's not, we're going to take a little less. If it's 0, if alpha were 0, we take none of that into consideration. We just leave the weight fixed as is. And then the actual value itself is part of that calculation, right? So this is really how much of the incorrect answer are we going to, or how much of changing a wrong answer to a right answer are we going to account for in our new weight? Does that make sense? All right, so let's try this. And this is the whole update rule for a perceptron using the Heaviside function. If we use a different function, which we often do, there are other functions that we can utilize, and that will change what the update rule looks like. Right? Because again, what happens here? It's either on or it's off. What happens in real situations? In real situations, maybe a neuron fires weakly. It just says, I got some input. But what might happen if you had a whole collection of these, a bunch of things firing weakly might be enough to trigger something else to fire more so. And it might change the output at the end of several layers maybe. Right? So we have something that is, oh, look at what happened. It's not very much. It completely gets ignored. Then later on, there's no evidence that that ever happened. But, oh, look, this little bit of stuff happened, and it's just enough to remember it and feed forward, then maybe that has an effect and changes the result. So even if you're thinking about looking at a digit, oh, you know, it's a 9, but part of it is really faint. If you completely ignore that, it might eventually be mistaken for a 0. I mean, if enough of that line was really faint, and you just kind of ignored it, but you don't want to ignore it, right? You want to notice it a little bit that it's there. And so other things, right? Or it's a 9, but the top part is really faint. I can't draw faint with, but so it's like the top part's really faint, and then the rest of it looks like that. If you completely ignore that faint part, then it looks more like a 4. Even if it is still rounded here, if it's completely ignored, that's more of a 4 than it is a 9, and it would be mistaken for a 4. Whereas if it was just enough to notice and those neurons are firing but not full on, then the other thing that can happen with this approach is that if it's not just zeros and ones, then the outputs aren't just zeros and ones. The outputs are maybe decimals themselves. And so the output might be something like 0.8, which would mean maybe you're 80% certain that it's true. Or if you had multiple outputs, it's a 0.8 here and a 0.2 there, you're 80% certain it's that category and 20% certain that it's that category. And if you had some other categories and they're all zeros, then you know it's not one of those. Right? So sometimes those kind of, but that can't happen with the Heaviside function because the Heaviside function is either all on or all off.
So how many perceptrons have multiple outputs?
Okay, so it's only still going to have one output, but it can have a decimal output by changing the function. And so one kind of change of the function is what's called the logistic function. The logistic function is instead of that h function that we had, is one that looks something like that. And so the graph of this function looks more like this. So grows very slowly, then there's a period of growth, and then it levels back off again. And so what happens, you could get an output of different values. So it's not just 0 or 1. It's not a step function like Heaviside is. It has the stuff in between. That's a Z. Yeah. And that is the dot product of the X and the W is what's going to go in there. We'll come back to that and we'll talk about that. And then there's a whole bunch of other situations. There's sometimes people will look at a system like this, where it's 0 up until 0, and then there's a straight line that may top out or not, depending on what else is going on. Other kinds of shapes, there's tangents and all kinds of other shapes that are possible for functions that get used a lot. Pros and cons to different methods depends on how the learning rate change, not this learning rate, but how quickly something learns, even with the same learning rate. It can depend on the function that you chose. This logistic function, usually if somebody's using that, you'll see the term, instead of just perceptron, you'll see sigmoid perceptron. If you see that term, then they're using this logistic function, or sometimes they'll say a logistic sigmoid, because there's other things that count, or that term gets used for as well. But we can change this function out. But if we change this function out, then the amount of error changes, because that's a more complicated function. It's not just, was it this or that? Now there's other stuff going on, and we have to use calculus and other things that happen with derivatives and so on, which we will talk about, but not just yet. So let's see what happens if we make up some weights. See, I did this with some bad choices. I did this, at least partially, and just put -1 on everything. Now, what do we know about that? Not going to be good, right? But let's just see what happens. All right, so we're going to update this. And how do we update this? We update this by using using the training data. And often what we would do is go through the training data in order, in some kind of order, and make all the updates. And then maybe go through the training data again. Maybe even you go through one training data point a bunch of times. Right? You end up going through all the data a bunch of times. Right? There's a lot of training with the data until what happens? Until either the weights don't change anymore, even if the answers aren't right, the weights don't change anymore, or the weights all change, or the weights don't change, and you get the right answer every time. Now, there's an issue with overtraining. Right? We can sometimes overtrain. If you overtrain, what happens? Then if you went to a new context, it's designed specifically to fit the old data, and if you have something that's a little bit different, then it gets it wrong. But in our case, for OR, I mean, there's only 4 points, right? There's 4 data points. But we can keep training on those 4 data points until it eventually turns these weights into, if not the weights that we came up with before, at least it turns into weights that work. Question earlier?
My brain had like 3 series of ones, and I forget most of them. But one of them was, so like, in this case, you could overtrain it by only showing like 1, 0, 1.
Yeah, so if we just focused on one data point and trained it just for that one data point, then it could get it wrong on the other data points. So that would be kind of overtraining and then not applying. But in this particular case, we have 4 points that we could keep testing those 4 points. Now, would we ever do this in a situation where there are only 4 possibilities? This isn't how you use the perceptron, right? But this is how you train a perceptron with enough data for whatever case that we're talking about.
My second one was, you mentioned even when you're training it, it gets the wrong output, but the weights don't change.
That was what I said at that point was if alpha were 0, if alpha were 0, it got the wrong output, but that part is 0 times, so the weights wouldn't change. It wouldn't update because that would be if that were 0. What could happen is you could have the wrong answer and that be 0, and it still doesn't change. So sometimes you have the wrong answer and it doesn't change for a different reason. But it doesn't change with that data point. So that data point doesn't pick up that weight, but maybe it picks up a different weight, or a different data point picks up the corresponding weight. All right? So let's see what happens. So let's pick an input value here, a training value, 1, 0. Okay, so we're going to train this with 1, 0, 1, and let's see what happens. So W1 is going to be the old W1, which was -1. I said when I ran this partially through by hand last night, I put alpha is 0.2. So just a number, right? 0.2. Okay. Now, with this data point, what is y? What's the correct answer? The correct answer is 1. What would the h value be in this case? So it would be -1 minus 2. That's a negative value, so h gives 0. And then what is the xi? It's 1. All right, so what happens? This answer was as wrong as it could be. And so what are we going to do? We're going to update with 20% of the difference. Now what if we made this number bigger? We'll update with a bigger percentage of the difference. What if we made this 1? We would use all of the difference. So what will happen is if we update with all of the difference, this time it might end up changing that weight at other times. It might bounce back and forth. Other data points might change that. Maybe, maybe not. If we make it 0.2 or some other number, then maybe it has a little more time to settle into the right answer, and other things won't make such extreme changes with it. But you can get situations where this data point changes that weight to this, and this one changes it back. And then this one changes it back, and that one changes it again. And you get stuck in this infinite loop that doesn't properly update. All right, so what does W1 become? Becomes -0.8. And what do? We update that. Then we do the same thing to this value, and the same thing to this value. And that is the first time through with that training point. Then what do? Then we move to the next training point. Maybe the next training point is 1, 1. This order is wrong. And then the next one? I knew you were going to say that. So we have the 4 training points. We go through all of the weights with 1 point, then all of the weights with the next point, all the weights, all the weights. It includes the bias as part of the total. And then do what? Then we do it again. Even with the same training data again. Just go through it all again. Go through it all again. Go through it all again. All again. All again. All again. How many ever times it takes until, again, our stopping criteria can change. It can be no more updates in the weights, or something, right? Or we see the same weights that we've already seen. Some kind of situation.
So, would there be a difference, or a notable difference, if for the training data you kept it like, let's say 1, 2, 3, 4, you train 1, then train 2, then train 3, then train 4, and you just did that same, or if you mixed the ordering each time you like went through?
So if you had an alpha if you had the potential for getting caught in a loop, you might have an issue with the order that you go through the data. I can't think of a situation right off that it would have an effect. Usually what you do is you just have your data and you just run through it in the same order every time. Could I'm sure we could create weird things by changing the order and create something where these 2 particular pieces, especially with a not so well chosen alpha, could cause problems. Sometimes what we do to help alleviate that is, rather than fixing a number alpha, we fix a number. We have an alpha function that early on maybe has a big value. And then as we go further, that number gets smaller and smaller. So what would that correspond to? That would correspond to like a learning curve, where early on you learn a lot and then you slow down how much of a change you have. So it kind of corresponds to that logistic function from earlier, right? A learning curve where you say, early on, when I haven't had much input, I'm going to make big changes to my weights. But after I've gone through a few times, I'm going to make smaller and smaller and smaller changes to the weights. And that can take care of some potential problems. So alpha doesn't have to be a constant. It can be a kind of a decreasing function that would change then the learning. The function wouldn't look like that, but the learning changes would kind of zoom in a little, or approach more cautiously, right? Make big changes when you don't know much. You learn a lot. But then the more you know, the less likely you are to make those kind of corresponding changes. So we've made one update. What happens when we get to the y? We're still on this one. We want to update W2. We go through it, right? What happens? W2 would not change this time because the input is 0. So this particular data point doesn't change the W2 weight. Does that make sense that it doesn't change the W2 weight? Why? Why does that make sense? Because there's no input on the W2 part, right? There's no input there. So if you don't have any input there, you shouldn't be making a change on that weight. You should only be making a change on that weight when you have something to contribute. And so the process takes care of that for us. It says if you didn't have any input, you don't get to have a say about the weight. Now, what if these were higher level, and so it's not just zeros and ones, and you had decimal? Then it might be that the decimal isn't big enough to make a difference. Or maybe it's big enough to make a very tiny difference, but maybe not enough of a difference in terms of the overall. So all those kind of things are part of it, right? So maybe a tiny, tiny thing doesn't have as much, a tiny value here doesn't have as much of a change, even though alpha is really big, it still might not change the weight very much. But if you had something bigger here, it might still overwhelm even a very small alpha and make a big change. And so that's part of the situation. But what's going to happen in these updates? Some of these will, when they will only update the weight that corresponds to there actually being an input there that's not 0. And what eventually will happen? If we have this 0.2 rate, then we're going to update things negative 0.8, then it'll go like negative 0.6, and it keeps going. And what will eventually happen? Eventually, we will get a line that separates the true statements from the false statements. Will it be the line we came up with?
Depends on our output.
Well, no. Let's see. Our line had a 1/2 in it, and at 0.2, it's not going to be the same line.
It depends on our alpha size that we run it.
Well, it does depend. Well, I mean, the alpha in this case, the alpha was 0.2, and so it's not going to get there. But with different alphas, we could get the same one, even starting with the negative ones across the board. Now, what happens if we knew going in? Oh, in this situation, we need all the weights to be positive except bias. We need to be negative. Then what might happen? We might be able to converge to an answer faster. But we don't always know that. And sometimes we will make those mistakes of assuming something about the weights that turns out not to be true about the weights. So what is all of this? All of this is really just creating an equation for a line. Or maybe for a plane, or maybe for something higher dimensional. But what are we doing? It's the idea of a linear separator that says in whatever dimensions we're in, we're able to create something that can separate category 1 from category 2. So the general then neural network idea is glue a bunch of these together. All right, so what I would like for you to do is to see if you could take that complicated XOR picture that we drew and draw it more efficiently, right? Have something with fewer, if we're thinking of it in terms of automata kind of thing, fewer states, right? Let's draw this with less going on. All right, so again, as usual, any questions, Discord, email, wherever, stop me, ask questions at any point. We will have a lab to incorporate incorporate this, and then what happens if we change the function. So I will give you those pieces, and then if you're using a neural network in your project, you have a building point to go from, rather than us waiting until the end of the term and be like, oh, okay, I still need to learn how to build a neural network. If you're not using a neural network in your project, and that's perfectly fine as well, there's other tools that we're going to be developing over the next couple of weeks.